Hello friends, in this lecture we will talk about flat top sampling. Recall that sampling is the process of obtaining a discrete time signal from a continuous time signal. We have already seen the process of ideal sampling and one way of practical sampling called natural sampling. Today we will look at another more practical method of sampling called flat top sampling. This sampling is known by two other names also, sample and hold sampling and pulse amplitude modulation or PAM. A simple circuit to obtain a flat top sampled signal is shown here. It comprises two switches K1 and K2 and a capacitor C. The continuous time signal m of t is applied at the input here, and the capacitor voltage is the output sampled signal. We denote that by m subscript p of t. The process is as follows. Initially, the capacitor is discharged. Then at a given time instant, say t equal to 0, switch K1 is closed momentarily while K2 remains open so that the capacitor charges to a value equal to the message signal's amplitude at that instant t equal to 0. So it acquires this value. Then K1 is open, K2 also remains open, so the capacitor voltage is maintained at this value. After capital T time, the switch K2 is closed, K1 remains open so that the capacitor discharges and acquires 0 voltage. Now both of the switch remain open until Ts, and then K1 is again closed momentarily so that the capacitor charges to the new value of the message signal at that instant Ts. K1 is again open, K2 remains open so that the capacitor voltage is held constant for capital T duration, and then K2 is closed momentarily so that the capacitor gets discharged, and K1 and K2 are again open so that the capacitor voltage remains 0. Again after Ts, the whole process is repeated, and that is how we get a sampled version of the continuous time signal m of t in the form of m subscript p of t, as shown here in the form of these pulses whose tops are flat, and that is the reason why this type of sampled signal is known as flat top sampled signal, and the corresponding process is called flat top sampling. Also note that since in this process we are taking the sample of the signal at a time instant and then holding the value for t seconds, and therefore this is also known as sample and hold sampling. Another way of looking at it is that we have a periodic pulse train which is modulated by the message amplitude at the sampling instance, and therefore it gives rise to a pulse train in which the pulse amplitudes are proportional to the message amplitude at those instants where the sampling is done, and that is the reason why it is also called pulse amplitude modulation or PAM. We are interested in looking at the spectrum of this flat top sampled signal and also look at whether the sampling theorem holds for this type of sampling. For that, we need to develop a mathematical representation for the flat top sampled signal. For that, we think of a basic pulse p of t, which is of height 1 and duration capital T, as shown here. Note that in terms of this pulse p of t, various pulses in the flat top sampled signal can be mathematically thought of as follows. If we look at this particular pulse occurring at t equal to 0, it is m of 0. The amplitude is m of 0 into the pulse p of t, the basic pulse that occurs at t equal to 0. If we look at this particular pulse, the amplitude of this pulse is equal to the message amplitude at the instant capital Ts. So m of Ts into the pulse p of t minus Ts. This pulse pt shifted to Ts. Similarly, this would be m of 2Ts, p of t minus 2Ts, and so on. Note that the pulse width t, capital T, is much smaller than the sampling interval Ts. We'll look at the consequence of this as we proceed. So the signal MPT, the flat top sampled signal, can then be represented as a summation of NTS, the message amplitude at the integer multiple of Ts, times the basic pulse PT shifted to NTS, where NTS is the nth sampling instant. So this n varies from minus infinity to plus infinity in general. Let us write it once again. So we have MPT equal to summation m of NTS into p of t minus NTS, with n varying from minus infinity to plus infinity. Now this can further be written as summation n from minus infinity to plus infinity m of NTS. Now pt minus NTS can be written as delta t minus NTS convolution p of t, using the basic property of convolution that when a signal is convolved with shifted impulse, we get the shifted signal. And now if you look at this closely, we observe that summation n from minus infinity to infinity delta t minus NTS is nothing but an ideally sampled signal or impulse train sampled signal or instantaneously sampled signal that we denote by m delta t, and that we have seen in one of the previous lectures. Accordingly, MPT can be denoted as m delta t convolution pt. That is to say, mathematically, we can look at flat top sampling as the convolution of the ideally sampled signal with the basic pulse pt that we have shown here. This is the basic pulse. It is pictorially depicted here. The message signal is ideally sampled to yield m delta t, which is applied to the pulse p of t, and the result is MPT, the flat top sampled signal. Now we are interested in looking at the spectrum of MPT, and for that we first need to look at the spectrum of P of t. Let us do that. So P of t is a rectangular pulse. So recall that if we have a rectangular pulse rect t by capital T, which is the rectangular pulse from minus t by 2 to plus t by 2 by 1, then it has a Fourier transform E sync ft in our case. The basic pulse pt is shifted by t by 2 so that it is from 0 to capital T. So applying the frequency shifting property, our basic pulse pt, which is the shifted version of rect t by capital T. So it is 0 to capital T. Using frequency shifting property of Fourier transform, it would be T sync ft e to the power minus j2 pi f into t by 2, the amount of shift, and that is equal to T sync ft into e to the power minus j pi f capital T, because this 2 and this 2 cancel. Let us call it P of f. Now we are interested in the magnitude of P of f. So the magnitude of P of f is equal to the magnitude of T sync ft, because the magnitude of e to the power minus j pi ft is just 1. Let us try to sketch this. So it looks something like this. Magnitude of P of f, which is T sync ft. So it is magnitude T at f equal to 0, and the 0 crossing occur at 1 by T minus 1 by T and so on. Note that because T, the pulse duration, is much smaller than the sampling interval Ts, 1 by T is much larger than the sampling frequency Fs, or 1 by Ts. Now note that MPT is equal to M delta T convolution PT, and convolution in time domain is multiplication in frequency domain. So we can write MPF, the spectrum of the flat top sampled signal, is equal to M delta F, the spectrum of the ideally sampled signal, into the spectrum of the pulse PT. Or if you are looking at just the magnitude, we'll take the magnitude of these. So MPF, the magnitude, is equal to M delta F magnitude times PF magnitude, and the spectrum then looks like this. Let us assume that MT is a band limited signal, band limited to W Hertz, with the basic spectrum as shown here, and the ideally sampled version of the spectrum would be the repetition of this basic spectrum at integer multiples of Fs as shown here, and this M delta F must be multiplied with PF, the spectrum of the basic pulse, which is of the sync nature, and when these two are multiplied, in effect what we get is this. Still, as long as this is, it should be Fs minus W, Fs minus W, and this is W. So as long as Fs minus W is greater than W, that is Fs is greater than 2W as per sampling theorem, we can still use a low pass filter to recover this part of the spectrum. However, note that this spectrum is not exactly same as the original spectrum. Because of the multiplication with this sync function, the higher amplitude parts have undergone more attenuation compared to the lower frequency part, and this effect is known as aperture effect. It results in some distortion of the original signal when we reconstruct the signal using a low pass filter. This is a drawback of flat top sampling. However, this aperture effect is negligible if the pulse duration capital T is much smaller than the sampling interval Ts. As a rule of thumb, if T is less than or equal to 0.1 times Ts, that is 1/10 of the sampling interval, in that case the aperture effect is almost negligible, and what we recover is almost same as the original message signal. However, in case the aperture effect is not negligible, then we have to have a device known as an equalizer with the transfer function, which is the reciprocal of PF, put after the low pass filter, and then this equalizer will nullify the effect of this PF, and therefore it will get the original signal back. So that is the use of an equalizer when the aperture effect is not negligible. We have to use it. In case aperture effect is negligible, then we don't require any equalizer, and just a low pass filtering would get us back the original signal. So that's all for this lecture. Thank you.